Good morning, everybody. Hello, I hope you enjoyed extended holidays. I mean, at least in Poland, we had some long weekend, probably call it bank holiday in England. Now, as usual, I have to go back for just a while into the previous semester because I want to add some elementary facts about graphs and paths and morphisms. If you remember, we defined a graph homomorphism in a natural way. And then we said that this graph homomorphism includes a map between the space of finite paths, okay? And now I want to convince you that with precisely this definition, which I explained a week ago, I believe, you actually can view FP as a functor from the category of graphs with morphisms being just graph homomorphisms to the category of sets and maps, okay? So now let me explain a little bit in more detail what I mean. So we have this category of G of graphs and graph homomorphisms. And now why is the functor? Well, this is a very obvious calculation, if you can call it a calculation, observation. But the only thing that we really have to check, something which I didn't say before, is that indeed this functor FP preserves the composition of morphisms, okay? So let's just have a look at it very quickly. How do I compose two graph homomorphisms? Well, I compose them component-wise. So F0, F1 composed with G0, G1. This is precisely F0 composed with G0, F1 composed with G1. So you just do it component-wise. And now I want to evaluate it at arbitrary path P in the graph E. So I apply the definition, which I just showed you a second ago on the previous page. I apply just this definition. And here I have to say separately what happens when P is a vertex and what happens when P is a positive length path. So when P is a vertex, this is just F0 composed with G0. When P is a positive length path, I apply F1 composed with G1. I see that there is one parenthesis missing. Yeah, so you see here there should be a parenthesis. I will correct it later on. So I apply F1 composed with G1 component-wise to each and every edge, which makes up our positive length path P, okay? But now we can see that this is exactly the same as composing the induced morphisms on the space of paths, right? Because what does it mean to apply FP of G0, G1 to path P? That's exactly given by the formula, except that you have only G's, G0 and G1 over there. And now when we apply FP of F0, F1, well, this is just applying F0 in the first case and F1 in the second case. So this formula is obvious. And now we can see that this assignment FP, which we define here, respects the composition of morphisms. So it is a functor, and because it doesn't change the order of morphisms, this is a contravariant functor. And I know that this is a completely trivial remark, but we are just about to start studying push-outs in the category of graphs. And it's very crucial here to see how this functor behaves with respect to push-outs. Because to my surprise, I discovered that it does not preserve push-outs without additional assumptions. So the situation is getting interesting. Okay, then we discussed what happens in the case when we have proper homomorphisms or graphs. And here again, we can make the same comment. Well, by the way, I was hand waving before 2 weeks ago when explaining this point. So now I wrote it up to make it crystal clear. So let me go over it very quickly one more time. So the setting is very much as before, except that now I assume that I have proper homomorphisms for graphs, which means that both F0 and F1 are finite to one maps, okay? And then I claimed without writing down why, I mean, I spoke some words, but I didn't write it down, that the induced map, you see this F is the same as FP of F0, F1. Here I had to use some notation to make it clear what I compute, but it's a bit awkward to write such a lengthy thing, FP of F0, F1, so I just write F. And this is my understanding of the induced map. All right, so why is it a proper path homomorphism of graphs? I mean that this is a homomorphism of graphs, this is crystal clear. We understood it before already from this formula. Now, why is it proper homomorphism graph? So why is the induced map F proper, which means finite to 1? Well, so for starters, if P is just a vertex, then the situation is crystal clear, because then the preimage under F of a vertex is just preimage under F0 of a vertex, which is by definition proper finite to 1. So this preimage is a finite set. Okay, so the first part is obvious. There's nothing to it. It's a little bit more subtle in the second case when we apply it to when we take the preimage of a positive length path. Okay, so now let's just do it. We take P to be composed out of n edges, P1, Pn, so these are all edges, okay? And let's take Q, which is in the preimage of P, which simply means that f of Q is equal to P, that there can be many of them. We just want to show that there are finitely many such Qs. Okay, so, but remember by the remarks that we made earlier, that this is a graph homomorphism, so it preserves the lengths of paths. Okay, so because f of Q equals to P and P is of length n, then we have no choice. Q is also of length n. So we can write it as a sequence of compatible edges from Q1 to Qn. And now when we compute FQ, by definition, this is F1 of Q1, comma, dot, 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 up to F1 of Qn, right? And we know that this is equal to the path P1 to Pn. So obviously, we can now conclude that for every I, we have that Fi of Qi is equal to Pi. In other words, Qi must be in the preimage under F1 of Pi. But remember, by assumption, F1 is proper. F1 is finite to 1. So every Qi runs a finite set. So obviously, you cannot choose more paths Q than you can choose different edges that are in respective preimages. Okay, so therefore you can conclude that the number of elements in the preimage under f of P is limited by the number of elements in this Cartesian product. Because for every I can choose as many elements as there are in the set F1 preimage of Pi. Okay, I cannot have any more paths. So the number of elements in this Cartesian product, which is simply the product of elements in each and every of these F1 inverse of Pi, this is the limiting number. But of course, I'm not saying that there are as many paths, because I'm not saying that when I take an arbitrary edge in the preimage under F1 of Pi, then if I do it for all I don't have a guarantee that the end of Qi will be the beginning of Qi plus 1, right? So in principle, you have more elements in the set than you have paths that are in the preimage of P, but definitely not the other way around, okay? If you have any path which is in the preimage of P, then it must be composed out of edges, so that each edge is in the preimage under F1 of respective Pi. And because Pi's are fixed, this number is fixed, and this is the estimate which proves that what I'm interested in, notably the preimage of P under F, that this is a finite set. Okay, so this is an argument as I explained to you 2 weeks ago, hands waving, but now I wrote it down. Okay, I think this is good to visualize it and not just talk about it. All right, I hope it's clear. I mean, it's elementary, but we should do it carefully. And now I want to make a similar remark as I did before for maps which are not necessarily proper, and claim also that this is a functor. All right, so this is the last part, I believe, from the previous semester. So as before, right, because the composition of finite to 1 maps is a finite to 1 map, this means that it makes sense to restrict ourselves to morphisms that are finite to 1, because the composition will preserve it. So we have this category, we denoted it by POG, proper oriented graphs. So now I have proper graph homomorphisms as morphisms and arbitrary graphs as objects. And now this is a functor to the category of sets and finite to 1 maps, because as we just proved above, this map F from FPE to FPF will be proper, which means finite to 1. Okay, and again, composition finite to 1 maps is finite to 1. gives us a finite one map. So this is really a category, and FP is such a functor. So I restrict to the subcategory POG, and then I land in the subcategory in the category of sets where I have the same class of objects, but now my morphisms are finite one. Okay, so that's all what I wanted to tell you as far as things that were missing from 2 weeks ago are concerned. And today during recitation class, we will do these proofs of 5 and 6. Okay, so these are the exercises for today, but that's for a recitation class. And I believe that now I can go back to this semester and finish the proof, do the proof of a proposition. So let me just scroll back to the very end of the notes. Okay, so this is the proposition we are supposed to prove, and then I switch to the whiteboard and prove it for you. Okay, so recall, we have this category POG. I just said what it is. We have a functor which assigns to a graph E a path algebra. So this is an algebra over K. And now I have what I do with graph homomorphisms, with proper graph homomorphisms. Well, I assign to it a pullback map, which goes from, so this is a contravariant functor to B. So F star goes from KF to KE. It's just a morphism in the category of algebras over K. So this is just a homomorphism of algebras. And here I give the recipe for this map. Okay. I say that my proper graph homomorphisms induce a homomorphism of algebras, which is given on the basis elements of my path algebra by the following assignment. And here you can see that it's essential to know that F is finite to 1, as otherwise the sum would not be finite. Right? Because what I do, I take the sum over all Q's which run through the whole preimage of P of chi Q's. So for this to make sense, I must ensure that my induced map F is finite to 1. But that's what we just proved a while ago. So this is a finite one map, and this makes sense. Of course, now I have to prove that it really defines a contravariant functor, but that's what I'm going to do on the whiteboard. And now I also want to claim that if I restrict this same assignment to the subcategory given by graphs with finitely many vertices, so in other words, when I restrict my attention to unital path algebras, then, well, I also get a contravariant functor. So here I don't do anything to obtain this subcategory. I don't do anything to morphism, but just proper graph homomorphisms. I just restrict my objects to objects with finitely many, to objects which are graphs with finitely many vertices. Okay, so then this assignment obviously lands me always in unital algebras over K. And I denote the category of unital algebras over K as nu Ka, and now I have a contravariant functor into this category. But now, mind you, morphisms in this category are not just algebra homomorphisms, they are unital algebra homomorphisms. Okay, so I have to also prove that this F star preserves a unit. Okay, so now let's go to the whiteboard and explain the proof. So I suppose I kill it. And I stop sharing, and I start sharing. But now it's the whiteboard. As usual, we have to tidy up the Zoom because you have all these Zoom controls that cover your whiteboard, and this is not nice. And I know you don't see it because when I work with my collaborators on Zoom, I see perfectly nice whiteboard, and they complain, well, what a mess I have to tidy up. And what I see is a blank whiteboard. Okay, so let me now find where I have this proof in my notes. Okay, so for starters, so this is a proof of this proposition. So let me start with an obvious thing. This Oh, wow, I'm using, sorry, I looked up the wrong thing. Yeah. I'm sorry, I looked up the wrong thing. So something which I already said, but now let me write it down, that if F from FPE to FPF is finite to 1, then the sum is well defined. Okay, next, take any R in FPE, so path in E, and P in FPF, so a path in F. And okay, so take any. So for any such thing, we have the following calculation. I just apply the definition of my pullback map, F star of chi P, and I want to understand what it is. So I want to understand what it does on a path R. Well, and so I just do this definition, and I think here I changed the notation. So this should be Q, and this should be P. Okay. Yeah, because here I have a P and here's Q. Okay. So I write the sum over Q in the preimage of P chi Q, and I apply it to R. So remember, how do I see it? Which way do I see it? Recall that the definition of the path algebra, these are finitely supported functions on the space of paths. So this is the way I'm reading it. So now this guy is an element in the path algebra KF, and therefore it is a map from the space of finite paths in F to the field K. All right. And remember how these chi Qs were defined. These were characteristic functions. So basically what you have here is Dirac's delta. So I can write it down now as a sum, of course, over the same Qs. So Q runs still the preimage of P. But evaluating each and every of these chi Qs on R is just delta QR, Kroneker's delta. Okay, so then, sorry, this is P. I can write down that this is the Kroneker's delta between P and F of R. Well, let's see why. If F of R is not equal to P, this means that R is not in the preimage of P, which means that Q is always different from R, and then this should be 0. Okay, so the 0 case agrees. If F of R is not equal to P, then R is not in the preimage of P, and therefore Q is always different from R, so that sum is always 0. Okay, so now what happens when F of R is equal to P? Well, then R is in the preimage of P, so there is a Q which is equal to R, so one of these deltas will be 1 and all other deltas will be 0. So this agrees. Okay, but now, of course, by the very definition of characteristic functions on the space of paths, this is precisely the same as chi p evaluated at fr. All right, but this is the same as chi p composed with f evaluated at r. And this means that indeed this formula which defined f star is really a pullback. So this notation is not coincidental. Okay. So hence f star is the pullback linear map. F star goes from finitely supported functions on FPF to finitely supported functions on FPE. And the formula is that F star of alpha, well, it's not a definition, it's a computation. It's just alpha composed with F. So this is really, really a pullback map, okay? So now the contravariance is obvious. Because that's a property of all pullbacks. If I have F composed with G star, this is just G star composed with F star. That's just immediate from this formula, okay? It works for any maps between any sets. So now we have a contravariance, but what we still didn't prove that indeed applying, you see, so if I would have, instead of the category of algebras, the category of vector spaces of a field K, we would be done. This is a contravariant functor, right? Because we just computed exactly what it was. Obviously, this is a linear map. So it maps morphisms in the category of graphs POG to the category of linear vector spaces and linear maps. This is all right. And well, maybe I should also check that this respects the composition of. No, I'm sorry. No, this is what I do. What I do already here, right? So this proves that this respects the composition of morphisms in the contravariant way. Okay. This is the functor property. If it's a covariant functor, then functor applied to the composition of morphism is the composition of functor applied to the morphisms. If it's a contravariant, you have to switch the order, and this is precisely what I'm doing, what I wrote here. So therefore. Map F. I don't know why I cannot write here. I can do now. Is a contravariant functor to the category of vector spaces. So it means that what remains to be done, and this is a nice calculation, is that indeed this F star is a homomorphism of path algebras. That's not obvious. This has to be computed. Okay. So to check that yeah, F star is an algebra homomorphism, using the fact that F preserves the length of paths. We compute as follows. Of course, it suffices to do it on basis elements. So I'm taking an arbitrary path P and an arbitrary path Q, and I diligently compute. So F star of chi P, chi Q. Well, I just multiply out chi P and chi Q. So I have my Kroneker's delta here, TF of P, comma, SF of Q. Remember, P and Q are paths in F because the contravariant function. And here, of course, once I have my Kroneker's delta out, this is a number and the map is linear, I can do it. I still have F star, but now applied to chi PQ. Okay. All right. Now I apply the definition of F star. So this Kroneker's delta remains as it was. But here I have a sum over all R's that are in the preimage of PQ. And here I have chi R. Yeah, I simply have chi R. Okay. And now comes the very crucial step. This is the crux of the whole proposition, if you will. I claim, and I'm going to explain it why it is the case, but let me write it down first, that this is the sum, double sum, over R1 running the preimage of P and R2 running the preimage of Q. And here I put delta, Kroneker's delta, but in my graph E, so it will be TE R1, SE R2. And here I put chi R1, R2. Okay. And I believe that this is not entirely obvious, so let me explain why. So this is the place where we use this preservation of length. And let me write it as a side remark before I continue the calculation. So to justify this step, we'll use the following implication, that if TF, sorry, I just wrote it excessively badly. But if I have TF of P different from SF of Q, this implies that for every R1 in the preimage of P and R2 in the preimage of Q, the end of R1 is different from the beginning of R2. Now, why does this implication hold? Well, because the reverse implication holds. So if I negate the right-hand side, I'm basically saying that there exists R1 in the preimage of P and R2 in the preimage of Q, such that TE of R1 I'm having problems writing it down. Is equal to SE of R2. Okay, this is the negation on the right-hand side, but if this is the case, then obviously it is true that TF of P is equal to SF of Q, right? Because remember, this is a graph homomorphism. So if F of R1 is P and F of R2 is Q, and the end of R1 agrees with the beginning of R2, then necessarily the end of P must agree with the beginning of Q. This is just the property of F of F being induced by the graph homomorphism. Okay, so because the bottom implication is true, also the top implication is true. And why does it help us with what we just wrote above? Well, you see, when the end of P is not the beginning of Q, the left-hand side is 0. So now I want to ensure that also the right-hand side is 0. But this is done by this implication, okay? If this Kronecker delta vanishes, then this Kronecker delta vanishes for all R1, R2, where R1 runs the preimage of P and R2 runs the preimage of Q. This is precisely what I wrote here, okay? So we have at least one case verified. So now what we have to worry about is what happens when TF of P equals SF of Q. So this is 1. Okay, and now why this is equal to that sum? Yeah, that's a good point. Why is it equal to that sum? So now I have that the end of P is the beginning of Q. I must say this is not obvious to me now. Yes?
Because when we have I1 2 multiplication and it go if it was 0 and go by homomorphism to PQ, PQ must be 0, and when it's not it's equal, it's not 0. So
yeah, but you see, I'm trying to figure out, of course, chi. Okay, so this is chi R. All right. So obviously, this must be. I'm looking for all paths which are in the preimage of the path PQ. Okay. So sorry, I'm right. This is not obvious. I have to use the length. Without it, this doesn't work. So when I have that, so maybe let me write it. So you see, so this is why using the fact that F preserves the length, this is also used in this case. But now I have to go to the next page. So I have on one hand side, I have a condition in the sum R is in the preimage of PQ. And now we know that PQ is a path. Okay, that's the case we study. And on the other hand, we have the sum, we have R1, which is in the preimage of P, and R2, which is in the preimage of Q. But you see, I have that F of, and here we have chi R, and here we have chi R1, R2. So, well, okay, if R1 and R2 do not compose, that here we simply have 0. I believe that we do have a Kroneker's delta. Yeah, you see. So first, I'm choosing only paths that compose R1 and R2. Other things vanish from that sum. Okay. Well, now it's not obvious to me why there exists any pair. Okay, let's go back to this. Right. So all right. So I have f. I have r, and so I have f of r is equal to pq. But because the length is preserved, there must exist. You see, this is the argument. There must exist r1 and r2 such that f of r1 is equal to p and f of r2 is equal to q. They must exist, and of course, and r is equal to r1, r2, so they do compose. So that set is non-empty, right? So that set is non-empty. Okay, so that's, I guess, the end of the reasoning, because you see that this sum over here, it boils down to taking all paths R1 and R2 such that f of R1 is P, f of R2 is Q, and R is R1 times R2. These are, that's what happens in that sum. And this is precisely what we have on the right-hand side. Because I have R1 in the preimage of P, R2 in the preimage of Q, I have this Kroneker's delta, and here I have chi R, which is chi R1, R2. Okay? So that's, this is not so obvious. I mean, I'm simply unraveling the statement that the depth preserves the length of paths. Okay, so that's this equality. So we computed it up to here. And now I will continue this calculation. But now I jump to the next page. And well, I can now this is straightforward, but we still have to finish it. This will be the sum. So maybe I will just rewrite what I had on the previous page. So this is this R1 running the preimage of P, R2 running the preimage of Q. And here I have Kroneker's delta, TE R1, SE R2. And here I have chi R1, R2. But now that's just the multiplication formula. So I can write it down as the sum over R1 running the preimage of P, chi R1 times the sum over R2 running the preimage of Q, chi R2, right? Because when I multiply to sum, I have a sum over two indices, and then I have chi R1, R2, but chi R1, R2 is precisely this Kroneker's delta times chi R1 composed by 2. Okay, so this is immediate by the definition of multiplication in path algebra, but this is by definition of my functor, of my f star. That's just f star of chi P times f star of chi Q. And we are home and dry. Okay, this is a star homomorphism. Sorry, this is a homomorphism. Jacek, you look puzzled. Do you agree?
Yes, I was just wondering about this.
Okay, because it's subtle, you agree. This is not so, you have to think for a while. I mean, all of these things are elementary, right? But the logic is not so completely trivial. Okay, and now we have just one more thing to do. So now we proved the first part of the most important part of the proposition, that we do have a contravariant functor to the category of algebras of field K. Now, how about unitality? So now we restrict. So finally, we restrict our attention to graphs with finite zeros, and check the unitality. So I compute f star of sum over all v in f0, iv. But now this is by definition sum over all w's in the preimage of f0. So you see what I'm doing, I should take for every chi v, I should take the preimage of chi v. But if v runs f0, but I'm taking the preimage of the set. Okay, so this is my complete sum. And here I have chi v, chi w, sorry. So this is one in, this is one in the path algebra KF. And now I claim that this is one in the path algebra KE. And the last equality follows from the fact that the preimage under F0, the preimage under F of F0 is the whole E0. Right, this is because we assumed that vertices are mapped to vertices, okay? So all vertices in E0, all of them are mapped into vertices in F0. So I take the preimage, of course, I get everything, yeah? Okay, so this ends the proof. And I must say, I really like this proposition. Maybe we should call it a theorem because it's cute. And now we are almost ready now to move to studying pushouts of graphs yielding pullbacks of path algebras. And that's what we are going to do starting in the next lecture in a week. And in the remaining 47 minutes, I would like to do a topic which is not very much relevant to the path of this lecture course, but it's a very important topic. I mean, for many people who do path algebras, that's the motivation of doing path algebras, completely different from ours. So please allow me at least 45 minutes on this topic. It is typed up in the lecture notes. You can view it as a side remark. I find it interesting in itself. You see, so this is this strain of reasoning where people classify finite dimensional algebras over a field, where they classify representations and so on and so forth. So this is very, very useful for people in plane algebra, very fundamental. I'm not going to go into these details, into all these things that you can claim once your algebra is finite dimensional and so on and so forth. I want to do it in full generality because I'm not making any big theorems about it, but I would like you to understand the paradigm. And this is about representation of graphs and the induced representations of path algebras. Now I have to find appropriate notes because this is something which I put much earlier in the text. It's been all the time. I mean, most of it was for a long time in the lecture notes, but I just didn't speak about it. And I have to find the right page. Yes, I think I've got it. Okay. So you can title it representation theory of path algebras. First, we need to define what is a representation of a graph. The definition is straightforward. I mean, if you were forced to come up with this definition, you would come up with precisely this definition. So let E be a graph, surprise, surprise, and K be a field. A representation of the graph E is a pair. First, we have a family of vector spaces labeled by vertices. And then we have a family of linear maps labeled by edges. So now I have to explain it. So VV is a K vector space. And that's all. You don't need to know anything about this vector space. It's just a vector space. Finite dimensional, infinite dimensional, whatever, you don't care. Can take K equals C, can take a Hilbert space. It's also okay. And now what is important is what are these homomorphisms, and most precisely from where to where they are defined. So phi E is, sorry, lowercase e, is a linear map from vector space which lives at the end of the edge E to the vector space which lives at the beginning of the edge E. And that's all. I'm just telling you the domain and the counter domain. Any homomorphism is fine. 0 is also a homomorphism. Okay. So this defines a representation of the graph E. And now please note, yeah, and I should maybe, well, it's not part of a definition, but in order to say how we induce a homomorphism of algebras, a representation of algebras, I also have to say what we do with vertices. So to each vertex V, we associate the identity map on this vector space with the label V. Okay. And I'm doing it in order to define the induced representation of a path algebra. Okay, so I have representation of a graph, and well, I can just say that. So I'm basic. I already told you what maps, linear maps, I assigned to edges. These are maps from a vector space at the end of the edge to a vector space at the beginning of the edge. And now I have to tell you what happens with zero length paths and positive length paths, right? So that I can tell you what kind of maps I associate to arbitrary paths. Okay, and then I will be able to define a representation of the path algebra, because the basis of a path algebra is labeled by all paths. So right now I only know what happens at edges. I also have to know what happens at vertices and paths longer than one. Okay, so this is what I'm defining right now. And to each positive length path in E, we associate the composition of homomorphisms assigned of edges. So if I have a path P composed out of edges E1 N, then phi P is by definition the composition of homomorphism assigned to edges. So phi of E1 composed with phi of E2 dot phi of En. Okay, and you can nicely see it on a picture. Here I have my vertex V0, my vertex V1 dot my vertex Vn minus 1 and my vertex Vn. Okay, so E1 is an edge from V0 to V1. And yeah, okay, so maybe I'll write it like this. This is E1 and this is En. But now I have here my vector space VVN, VVN minus 1, VV1, and VV0. Okay, remember the definition. The homomorphism goes from the vector space which is at the end of a path to the vector space which is at the beginning of a path. So here is my phi En, and here is my phi E1. So you see this composition, it makes perfect sense, because first I apply phi En, then I apply phi En minus 1, and so on and so forth. Okay. So it makes perfect sense. I mean, these things really compose. So having said all of this, I can now define the induced representation of my path algebra, but first let me remind you the definition of a representation of an algebra. So let A be an algebra over a field K. A representation of A is an algebra homomorphism from my algebra A to the algebra of endomorphisms of some vector space V. Where V is a K vector space. Okay. So now, in order to define the induced representation of a path algebra, given representation of its graph, I just have to build up a vector space V. I take the algebra of endomorphisms of a vector space, and I have to construct for you an algebra homomorphism from my path algebra KE to the algebra of endomorphisms of V. Okay. So that's precisely what I'm going to do. I'm now taking A being the path algebra of a graph E. We obtain a representation. We obtain representations of A from representations of E. We obtain representations of A from representations of E. In the following manner. So first, I have to give you a vector space, and I can define it as the direct sum over all vertices. Oops. So V runs E0, and here you have a VV. Okay. So that's by definition my vector space. And now my representation, in order to define it, I suffices that I do it on basis elements. And basis elements, remember, are these chi p's. So rho of chi p. So rho of chi p now must be an endomorphism of my vector space V. So now I take an X in my vector space V, and I'm telling you what the result is. Okay. And the result is as follows. It's just 0 if X is not in the direct summand labeled by the end of P. And it is phi P of X otherwise. Sorry, this is supposed to be not. All right, so if X is in the direct summand of my vector space V, which is labeled by the end of the path, then I apply phi of P, which makes sense by the definition we had before. You see, the morphism, homomorphism phi P is a homomorphism from the vector space at the end of the path to vector space at the beginning of the path. But X must be there, otherwise I just put it to 0. Okay. So, well, obviously this is a linear map. So obviously I can now claim that rho of chi p is an endomorphism of V. Right, because in order to define a linear map, it suffices that I define it on. Okay, that's I wanted to say something wrong. I just define it directly here. Okay, maybe I should check the linearity, but I suppose the linearity is obvious from the definition. So because, well, if I write so I'm not checking now that rho is an algebra homomorphism. That's the next thing. I'm just checking that rho of X P is an endomorphism of V. Okay, so I have to do this. Yep. And when I do this, I just apply this formula. Okay, so this is 0. for x plus y not in VTP, and it is phi p of x plus y, which is yeah, and here we have. Oops, I didn't think it over, to be honest, because we might wait a second. I have to remember that this is a direct sum, okay, and yeah, this is a little bit too awkward. So when I have a vector space given as a direct sum of its vector subspaces, in order to define a linear map on such a vector space, it suffices that I define a linear map on each and every of these subspaces that then assembled in the direct sum giving the whole vector space. This is sort of like the linear independence. It's like you can always define a linear map by assigning whatever you want to the basis elements. So on for every VV, I can choose any linear map I want. And then to get a linear map on the whole vector space V, I just add them up. Okay. So in fact, all I have to do is to check the linearity of rho of XP restricted to some direct summand. Okay. So I'm assuming here that both X and Y are in some vector space VV. Okay. And this means that, of course, also x plus y is in this vector space VV. So if V is not T of P, it's just 0. Okay. And if V is equal to TP, then this is just, remember, this is an algebra this is a linear map. So this is phi P of X plus phi P of Y. And this is what happens for, maybe I can now write it like this. Here I put a comma, because by assumption I'm taking X and Y from the same vector space, okay? So this is what was my problem. So I put a comma. So they are both not in a TP. And the other case is when they are both in TP. On VTP, sorry. And of course, a mixed case is when X is in VTP, but Y is not, or the other way around. That's excluded because they're in the same direct summand by assumption. Okay. So in other words, either V is equal to TP or V is not equal to TP. That's what we are considering. And now you can see that this is obviously rho chi P of X plus rho chi P of Y. Right? Because if X and Y are in TP, are not in TP, then we are just in VTP, then we are just adding up zeros. And 0 plus 0 is equal to 0, so it's all right. And otherwise, we look at the bottom formula, and this is just phi p of x plus phi p of y, which is precisely what we have here. Okay, and exactly the same with a scalar multiplication. When I take x in VTP and I multiply it by A, then AX is also in VTP, and then phi p is a linear map, so this will pop out. And if X is not in VTP, then A times 0 is still 0. So yeah, good. Okay. So let me just write much in the same way. What was it? 5. Rho of chi p. Yeah, I forgot the letter. Rho of chi p of AX is a row of chi p. Okay, so we have established that indeed for every chi p, row of chi p is an endomorphism of V. So if I take any finite linear combination of endomorphisms, this will be an endomorphism. So that's quite all right. But what I still have to prove that indeed this is a representation, that it is a homomorphism of algebras. All that I gave you right now is a linear map. This establishes a linear map from algebra A to endomorphisms. Okay, so maybe I will write it down. Hence, rho is a linear map, well-defined linear map. So what we were just checking, but it really lands in the endomorphisms of V, and it is well defined as a linear map because I'm just assigning values of rho on the basis of A. So it remains to show that rho is an algebra homomorphism. Which we just do by an elementary direct calculation. So rho of chi p chi q, again, it suffices to do it on basis elements. I apply it to X. Okay, so first I multiply in my path algebra. So I have my Kroneker's delta, TP as Q. And I have rho of chi PQ applied to X. I mean, this is sort of by definition. When I define rho by some assignment to basis elements, of course, when I apply rho to some linear combination of basis elements, this will be a linear combinations of rho applied to basis elements. So this sort of equality is by definition. Okay, and now I'm applying the definition of representation. So the Kronecker delta remains as it was. And now I have phi of PQ applied to X. Okay, but remember from the very definition of phi, now we can write it down as phi p composed with phi q applied to X. So for starters, if the end of P is not the beginning of Q, then phi q of X will not be in VTP. So phi p applied to it will be 0. So this is what will happen. This is this Kroneker's delta factor. So if the end of P is not the beginning of Q, then by the definition of phi's, we'll also have 0. So now what happens when the end of P is equal to the beginning of Q, then this Kroneker's delta is 1. And well, we really have that phi PQ of X is phi P composed with phi cube. That's again obvious by the very definition, because remember that phi PQ, where PQ is a path, it means that you write Q as a sequence of compatible edges, and you write P as the sequence of compatible edges, and then this phi PQ will be the composition of homomorphism assigned to all edges. Okay. So basically all that I'm using here is, I don't know, associativity of concatenation of paths, whatever. Yeah, so now this formula is obvious when P and Q match into a path. Yeah, because then phi Q lands at the end of P. I mean, it lands in VTP. Phi Q of X is in VTP. So phi P applied to it will be given by this non-trivial formula given by the composition of homomorphisms assigned to edges that altogether compose into the path P. Okay, so I think this formula does not require any more explanation, but now this is by definition of the representation. This is row of kind P composed with row of kind Q, and all of that applied to X. And because X was arbitrary, we finished the proof. Okay. Yes. Okay. I was a little bit so this does the job for the positive length. Yeah. So my argument was when P and Q are paths of positive length. All right, because that's this is a different formula. And now to be really rigorous, you have to verify it at 4 possibilities. So we just did PQ positive length, but P and Q can be both vertices or one of them can be a vertex. Okay, but then this is also obvious, because remember what we assigned to vertices, just identity maps. This was our assignment in the representation. So if you, well, basically I'm wondering which formula. Yeah, I guess that this is the crucial step. Okay, this is the crucial step because all the rest is obvious. You don't have to do it in special cases. So we need to verify it in 4. We need to verify it in 4 cases. So P, Q belong to the arrow ideal. P is a vertex. Q belongs to the arrow ideal. Then P is in the arrow ideal and Q is a vertex. And finally, P and Q, oops. And finally, P and Q are both vertices. So I just gave you an argument in the first case when P and Q are positive length paths. This was actually the most interesting part. And now when P and Q are both vertices, then by definition, phi P and phi Q are simply identity maps. And well, if P and Q are different vertices, then we just get 0. Well, you can argue what it means. Yeah, you can argue what it means. Okay, so this means that when I was telling you what we assign to vertices, in fact, we see, so that's the benefit of writing this properly. We actually assign the projection. No, a projection, or yeah, I guess a projection on the direct summand. Yes. So I erase it. So this is a projection from V to the direct summand VV. So the projection. This is a direct sum and projection, okay? So what I'm doing is on every component of V, which is not VV, I put 0. And on VV itself, I put identity, okay? Because otherwise I cannot make sense out of this formula when I'm verifying these cases. Okay, so what if I take two different vertices? Then the left-hand side, of course, vanishes. But how about the right-hand side? I cannot compose, right? But now I can. Now I can when I take them as projections. So if I have two different vertices, then these projections will multiply to 0. Yeah, because the image of one projection will be in the kernel of the other projection if these two vertices are different. So this will be 0. But now if the two vertices are the same, well, then basically I have, well, composition of two projections is just the same projection. And this would agree. Here I have 1 when the vertices are the same. Then V times V is V, so I have 5V of X. And here I have 5V of X, so I have this equality, all right? And now finally, we can do a case when, say, one of them is a vertex and another one is a positive length path. Well, then again, but actually here it's a bit simpler perhaps. Well, I know everything is simple here. If this vertex is not the beginning, if vertex P is not the beginning of a path Q, then of course the image of phi Q will be in the kernel of this projection, so it will be 0. So the equality checks. And if the vertex P is indeed the beginning of the path Q, then the Hajac delta will be 1. PQ will be just phi of Q. And here we'll have a projection applied to an element on which the projection is identity. So it will be phi Q of X. And now when I'm on the other side and I first apply the projection, again, if the vertex Q is not the end of P, then I have a projection onto the subspace, which is in the kernel of phi P, yeah, because it will be a projection on this vector space VV, but phi P is 0 on vector space VV if V is not the end of P. So that's all right, because yeah, I will just apply it to something which is in the kernel. I mean, when vertex V is not the end of path P, so this equality checks out. And when I do have at the end of P is my vertex V, then well, I'm just I have a projection on this. Yeah, that's actually, you see here I have to look at X. so here this verification is a little bit different because I also have to see what happens if X is in this vertex Q. I mean in VQ or it's not in VQ. Okay, if X is not in VQ, then phi Q of X is simply equal to 0, and we get 0 on the right-hand side. But the same happens on the left-hand side, because remember that Q is the end of P, and phi PQ is just phi P. And if X is not in VQ, then it is not in VTP, so phi P of X is also equal to 0, so it checks out. Now, if X is in VQ, then phi Q is just identity on X, it does nothing. And then I have phi P applied to X, and that's the same on the right-hand side, because PQ is equal to P, so phi PQ is phi P. And I have phi P of X equal phi P of X. Okay, so it was actually more complicated than I thought. So I'm happy that I checked it out. I wrote it in the lecture notes, just please verify 4 cases. But in fact, In fact, it takes a little bit of work, and these 4 cases are all different. But now it's done. We see that this is an algebra homomorphisms. Okay. So we proved that a representation of a graph induces a representation of its path algebra. I have one more sentence written here. Yeah, yes, but I sort of already took it into account. Yeah, this is what happens. I in the lecture note I assumed that the calculation goes for x in VTQ, but it's something separate when x is not in VTQ, and then basically you can immediately see that everything is 0. But I'm not sure whether I used it. I sort of used it at the very end when checking the last part. So I'm not sure I should write it. Yeah.
I think that you use it when you write IPQ applied to x, because otherwise you need to understand it as 0 if x does not belong to.
Yeah.
So I think that's the point where we.
Yeah. 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 So take x in VTQ, okay? Yeah, you're right. So if x is in VTQ, then this check I did with a projection is much easier, right? I mean, that's you know that phi q of x is just x, so I didn't have to say it. But basically what I said for this one of 4 cases, I have to say for all cases. So what happens? Yeah. So to finish the argument, so finally. Since the end of PQ is equal to the end of Q, we conclude that rho of chi P, chi Q of X equals 0, equals rho of chi P composed with rho of chi Q of X for X not in VTQ. Well, on that side is obvious because I will apply phi q to X. So if X is not in VTQ, that's it. It's gone. And here, remember, if PQ do not match, then I have 0 anyway. If PQ match, then I have a row of chi PQ. So X must belong to the end of PQ, but the end of PQ is the end of Q. So X is not in the end of PQ. So phi PQ of X is also 0. Okay. So this ends the proof that we have a representation of the path algebra induced from the station of a graph. So summarizing, a representation why does it stop? Of E induces a representation of its path algebra. And this is very helpful because this representation of a graph is something very tangible. This is something very constructible. And when you want to classify representations, well, then it's a little bit easier task. And if you, now why is the important representation theory of algebras? Because first what you do for, say, a finite dimensional algebra of a field K, you construct so-called Gabriel's quiver. And this is an oriented graph, and you take its path algebra. And then there is also, so this quiver is given by the datum of your algebra. And then also this datum of your algebra gives an ideal in the path algebra, such that the path algebra divided by this ideal is isomorphic with the algebra started with. And then you simply take a representation of the path algebra of the Gabriel quiver assigned to your algebra you started with, such that it annihilates the ideal. So now you simply solve some linear equations. Yeah, because you have some relations that define your ideals. And now when you cook up, you see here in the definition of representation of a graph, we could take any homomorphisms. Okay, that's it. Any family of vector spaces labeled by vertices and linear maps labeled by edges will give you a representation of graphs. But now we have some constraints given by your ideal. Ideal must be annihilated to yield the representation of a quotient algebra. But this boils down to solving linear equations. And this is how you can go around and say classify representations of the algebra, study the category of representations of the algebra. And by the way, a remark, Oscar, are you here? Oscar, are you here? No, I don't see Oscar. But you can question the choice of this assignment. I mean, why don't I go the other way around? You see, this is somehow arbitrary choice. I might have as well defined it like this, that I'm to an edge from V0 to V1, I assign a linear map from VV0 to VV1. And then here I would have to reverse the formula. It would be phi en composed with phi n minus 1 dot 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 up to phi e1. It also makes sense. Yeah. But you see, the thing is that somehow this would land me in the right modules. If you want what this homomorphism gives me when I define representation like this, okay, this makes V a left A module. That's just a custom. I mean, we usually look at representations in this way, at least, you know, in functional analysis, I suppose. These are left modules which you start, okay? But in algebras, they don't care. They just say, okay, for me, a representation of an algebra A is a module, right or left of A. So when you look into the blue book about path algebras, they do the other assignments. They do it the other way around because they map A into the representation is given by a right module of A. And when you have a right module of A, you can reverse it. Yeah. Then all makes sense. It is still a representation. It's just a question of switching between left and right modules. If I write it like this, so this this map rho, so rho renders the A left A module. Because I have a map from A tensor KV to V given by A tensor V is mapped into rho of A of V. Yeah, and you see that it's irrelevant where I put the number. So this is really defined on a tensor product, because if I have rho A lambda V, and this is just lambda rho A V, but this is the same as rho lambda A V. Okay, so this is really defining the tensor product, and then you can check the left, all the rest, the other conditions. I think Anya was telling you what modules are, so you know how to check it. So this is just a remark if you are surprised of why the formulas that I'm giving you are reversed with respect to formulas you have in the big blue book. All right, it's time to finish the lecture, and it's a pity because I still have one more thing. I wanted now to give you an example of a presentation and then to show you how to construct a faithful representation. But this would take, I don't know how long, at least 15 minutes, maybe more. So let me stop right now. And we resume at the 11:15, and I stop recording right now. Thank you so much.